Derby, say something. There we go.
Hello. We're all good? All right. Good morning, DerbyCon. Woo! Yeah. That's a lot of people for 10 in the morning. So I'm going to just throw this out here. I can do this talk, or we can have group nap time. What do you think? All right. Really happy to be here. Go to DerbyCon every year. This is my first year speaking here. I'm really proud to be here. This talk is Antivirus Evasion Lessons Learned, or my alternate title, 1,000 Ways Not to Make a Light Bulb. Off the famous Thomas Edison quote, of course. So, get this out of the way real quick on who am I and why do you care what I have to say? I can at least answer the first one. You'll have to answer the second one yourself. I'm David Maloney, aka Thelightcosine on the internet. You can find me on Twitter and IRC at Thelightcosine, and I'm on Freenode and the Metasploit channel. I am a Metasploit core developer. I work on both Metasploit framework and the commercial products. I am a member of the Coreland team, which is my distinct privilege and honor. I am a sometimes member of the Fail Association of Lock Sport Enthusiasts. Any of my fail guys in here? No? Oh, that's sad. I'm one of the founders of Hackerspace Charlotte and a former pen tester. Yes, former pen tester. I took an arrow to the knee. So, we don't have enough time for everyone to introduce themselves, but how about a show of hands here? How many people in this room are a noob? All right. Everyone who didn't put their hand up, you're deluding yourselves. So, I like to start my talks these days with a quote from HD. This is one of the first things HD ever said to me when I started hanging out in the Metasploit channel. I wanted to be upfront and said, you know, I'm really interested in doing this stuff, but I'm a total noob. And HD said, well, if you don't think you're a noob, you're not trying hard enough. And I think that's a really important thing for the InfoSec industry and community, is if you're not pushing yourself to do new things that make you a little scared that you're going to fail, then you're doing it wrong. You got to keep challenging yourself to do new things. The process for learning new things in my mind is, first you learn it, so you get somebody to help you learn, you read up on the subject, you find all the information you can, you internalize it. Then you do it. You practice it over and over and over again till it really starts to sink in. But you still don't actually know it yet. When you finally know it is when you start teaching it to other people. And that's really important. You have to do all three of these steps to really, truly know something. And if you haven't done all three of these things, you're probably still a noob. So, let's move on. Why are we talking about AV evasion? So, if you're a pen tester, this has probably happened to you at some point. You've gotten a shell, your exploit worked, and then 20 seconds, 30 seconds, a minute later, something happens and your shell dies. Chances are it was Antivirus caught your payload on the system and nuked it. Now, where this tends to be a problem is when we have to touch the file system. When we have a straight up memory corruption exploit, our payloads tend not to get detected, even though they're detected. You can upload that payload to any AV vendor you want, and you can see the detections. But when we're just inserting it right into memory, AV is terrible at finding it. So we haven't put a lot of effort into AV evasion in the past, partially because Metasploit and exploitation in general were very focused on memory corruption exploits. But the exploitation landscape is changing a lot lately. So where we're getting caught most of the time is when we're writing to disk. This is things like using ps-exec. I hope most people have at least a familiarity with using that module. any command injection exploits, anything that's going to write that payload to disk and then use some sort of method to execute it from disk. That's where we're really running into our problems. And a lot of the exploits and attacks that we see now require that. Memory corruption is not dying completely, but it's becoming less and less common to run into. So how do we get around this problem? Well, Metasploit has a series of its own unique challenges when talking about payloads. Number one is that we're a high-profile target. One of the reasons Metasploit gets flagged all the time right now is because all of our executables have been downloaded by all of the vendors and they write a signature for it. You can take the default executable template for Metasploit payloads and check it on VirusTotal. There's maybe one vendor that isn't flagging it even without a payload in it. So the next challenge is it must be redistributable. So there can't be any licensing requirements. It has to fit with our licensing scheme. It's got to be something that we can, that works within our code base and within our framework. And it has to make sense to deploy on a large scale. I've had a lot of people over the past years come up to me and say, oh, well, I'm using this crazy technique where I generate the payload and then I do all this stuff, I do this thing, and then I do this thing, and then the payload doesn't get caught. And that's great, and that works for an individual pen tester. Where it doesn't work is in the automated process of the framework. We can't easily shell out and do all these other things and then come back. It creates too many problems. So what works for an individual on a engagement by engagement basis, and there's plenty of things that do, doesn't necessarily translate into something that we can work into the framework itself. So I was going to try and find a clip from Monty Python's How Not to Be Seen here, but unfortunately I couldn't find a non-YouTube clip for it. So hopefully you're all familiar with it, but lesson one is don't stand up, right? We just said that if you don't touch the file system, you're not going to get caught, so avoid touching the file system if you can. And I'm just getting this out of the way. You know, memory corruption exploits are always a better way to go if AV is a concern. And if it's not, there's a lot of other tricks out there. The most prominent and successful one lately is the use of PowerShell. And I'm not going to go too in-depth in that because there's a lot of smarter people doing a lot of cooler stuff with PowerShell than me. You can check out the PowerSploit guys. Carlos Perez did a training class at the beginning of DerbyCon. But PowerShell gives us a lot of opportunity to execute code without ever writing anything to disk. So if you absolutely must touch the file system, don't panic. Don't hide, blend in. That's going to be kind of the theme for this whole talk, right? A lot of people are trying, when they do antivirus evasion, they're trying to hide. And what they really need to be doing is blending in. So a lot of people, they use obfuscators, encoders, encryptor packs, and it gets them good results, at least at first. And this is what they think they look like. Here's what they really look like. Yeah, it's going to work for a little while, but pretty soon you're going to get spotted, and then you're right back to where you were. So, real quick, we're going to just define some terms. Hopefully, everyone's familiar with this, but in the antivirus world, we're going to be talking about signatures, which is basically just pattern recognition on recognizable pieces of code. Heuristics are an AV detection mode where it's basically going to emulate execution of the program in some manner and try and come up with a match for the behavior of the program. And then there's sandboxing. And sandboxing is where it basically just creates an isolated environment where the program can execute, but doesn't really have full permission to do all the things that it might. So, some Metasploit terms. A payload, you guys can tell me to move on if you want, but payload is the code that an exploit actually delivers and is executed by the exploit. And when we're talking about a payload, it's often broken down into a stager and a stage. So a stager is the initial shellcode that we send that is small enough to fit in whatever buffer, in like a buffer overflow or any kind of memory corruption exploit, and it connects back to Metasploit and pulls down the rest of the payload, which is significantly larger. And that's what we refer to as the stage. So this distinction between stager, this distinction between stager and stage is very important when we're talking about AV evasion, because what initially gets sent down is that stager, and that's one of the key areas where we're getting flagged. So real quick, here's a nice little analogy for how you can think about a Metasploit payload. You've got your delivery system. In this case, I'm just throwing MSO8067 up as an example because it's everybody's favorite exploit. Then the exploit is going to put the stager, in our case reverse TCP, into memory. The reverse TCP stager creates a reverse connection back to our Metasploit handler and pulls down metserv DLL, which is the stage from interpreter. Metserv DLL then has a bunch of other extensions that it comes and pulls down and loads into memory on that box. So, yeah, this basically just goes through what we said. So the stager creates executable memory and then connects back, pulls the stage down, puts it in that memory and executes it. Now, in an EXE, this works slightly differently. The exploit method is just creating that RWX memory segment from the executable and then pulling our payload down and shoving it in it. So one of the big problems we have currently is that whenever we drop an EXE, that executable is just storing our shellcode in a variable somewhere. We send that executable and the payload is right there, recognizable inside a variable somewhere stored in memory. So the goal of my research in this talk was to discover specifically what detections we're triggering on. Everyone's been talking about different techniques, right? Talk about packers and cryptors or some clever little thing they're doing. But what I wanted to know was why some things work and why they didn't. So I took all the ways that people have talked about doing antivirus evasion and broke them down piece by piece and said, okay, how many detections do we get when we do this thing? How many do we get when this? So that we have a real understanding of what's going on when we get detected. So here, oh no, too far. So the process that I went through is that I use what's called Metasm. Is everyone here familiar with Metasm? Anyone? Okay, so Metasm is a wonderful Ruby library that is a assembler, a disassembler, a C compiler, a debugger, all in one. It's an amazing piece of software, and we can use it for wonderful metaprogramming in Ruby, and we use this in Metasploit. So what I did was I took each technique and generated C code with Metasm, compiled it into an EXE, and then automatically upload it to VirusTotal and pull those results down and sort them based on what the detection was. Nobody's screaming yet. That's surprising. That's right. I said VirusTotal. So there's some problems with VirusTotal. The vendors don't deploy all of their engines to VirusTotal, so your results on that site actually are not 100% accurate. Some of them don't put heuristics up at all. You're only going up against signatures. And the thing that everybody loves to scream about is that VirusTotal shares those results with the vendors. So if it gets flagged by one vendor but not some of the others, VirusTotal will redistribute that information to all the vendors so that they can sig the same thing. So why this doesn't actually matter for our process is that this is all strictly proof of concept, and if we can't survive this, then our technique is broken anyways, because we're doing the same thing everybody's been doing. Antivirus evasion, malware, all of this is sort of an arms race, right? We come up with something new to get past antivirus. Antivirus finds a way to detect it. We find something new, and we just keep going in this pattern back and forth, and nothing really breaks the cycle. So what I'm looking for is some way that we can break that cycle and do something that really just gets us beyond doing this same routine, the same song and dance over and over again. So the first question you have to ask is, where are these detections coming from? Well, the one we've been saying for years and telling people is the biggest problem is the executable template. So when we build an EXE in Metasploit Framework or Pro today, we have pre-built executables that are used by default. And it shoves our payload in there, takes that executable, sends it to the file system, and it just runs. Well, like I said, you can upload those templates with no payload whatsoever, and it still detects it as malicious on 42 vendors, which is really hilarious because our default template in Metasploit is the Apache Bench software, which is a completely legitimate tool. Yeah, the Apache guys probably love us for that one. The next place it's getting caught is the stager. Reverse TCP is an incredibly recognizable piece of shell code at this point, and it contains a common piece of shell code called block API that was written by Stephen Fewer, and most shell coders use block API. What block API is for is because when you're doing a memory corruption exploit, you don't know what the address of any of the Windows API functions are. You need a way to call those functions reliably and get the addresses for them. So block API goes through and actually tries to find a way to call those functions without already knowing what the addresses are. And it's a great piece of shell code. It's highly optimized. It's very small. The problem is everybody uses it, so every AV vendor knows to look for it. One of the things that I thought might be a problem was creating RWX memory. Creating executable memory at runtime sounds a little suspicious, right? I mean, it's not that easy to think of a scenario where a legitimate program at runtime is going to create a whole new section of memory and mark it as executable. Why would you do that? And then the last possible place that we are getting flagged is the encoder. And this is going to be a little important later, but I'm going to say this up front. Encoders do not evade antivirus. Once again, encoders do not evade antivirus. If you come into the Metasploit channel and say, my payload is getting flagged, I don't understand, I ran it through an encoder, I am going to hurt you. All right, so how do we get around the problem of the EXE template? Well, like we said, the default template with no payload is 42 detections. We have the ability for users to supply a different payload, a different EXE template. And any of the exploits that do executable drops actually have an advanced option on there called EXE template. So if you do show advanced in Metasploit Framework, you'll see that option. You can point it to a totally different template. Problem is, this still only cuts the detection rate in about half. And part of that is because of other things we're doing to the executable template, and some of it's because of the stager and so forth. So, first thing I set to do was fix our injector method. So, the way our injector works is it creates a new segment in the executable, which then calls virtual alloc to create RWX memory. And yes?
Sorry. Real quick on the template. My understanding was that it was an actual executable. Mm-hmm. Is it different from that? Is it manipulated in any way, or is it just an actual regular EXE?
It's a regular EXE. And in the case of Metasploit Framework, the default template is the Apache Bench tool, which is a command line tool for sending HTTP requests. So we have a couple of different ways of building EXEs, one of which is to inject, which preserves the original functionality of the executable. And what we did before was we would have this new segment, and the segment would call virtual alloc to create RWX memory and stick our payload in it and execute it. Well, that was getting flagged pretty quickly. So this is actually now in Metasploit framework. This is the only piece of this talk. I'm sorry. Not used to drinking coffee. It's catching up with me. This is the only piece of this talk that's already implemented in Metasploit framework. A lot of this stuff is not going to be directly implemented, but that's why I'm sharing the concepts with you guys. So what we do is we use Metasm to create a new RWX stub inside our executable. So executables are broken down into sections, one of which is the text section that contains the actual code that's executed. And so we just basically create a new text section in that executable. Then we take our existing payload and just basically decode it back into assembly instructions, shove it into that section. So, we have the ability to set a buffer register, which is part of the encoders for polymorphic encoding. It just basically just tells our encoder where the payload is in memory. And then we just write a little assembly stub around it that all it does is create a thread, execute our payload in it, and then jumps back to the original entry point of the executable. So what this looks like, if you run this executable, say we take calculator.exe, it's actually executing a totally different section of code that we've created, but all it does is spawn off a little thread in the background that you're probably not going to notice. Our payload runs in it, and then it jumps right back to the original part of the code the developer wrote. So your calculator pops up, and everything works as normal, but as long as calculator is up, you've got an interpreter shell running in the back. Pretty fun stuff. So that's, oh yes, there's some more technical details, but so this cut the detection rate from 41 detections for the injector method down to 14. Pretty nice, if you're not dealing with one of those 14 AV vendors. So gets us a little bit closer, but doesn't really solve the problem. Whoa, are my slides out of order? Oh no. What happened to my slides? Dear Lord. Okay, so some of my slides seem to have disappeared. I apologize. So what I said about doing was to cut through and just do some basic what's getting flagged. Is it the RWX stub creation? Is it executing the memory? Like what specifically is getting detected here? So I ran through and created a bunch of different executables, one of which the first one just creates read-writable memory at runtime. And that actually got flagged, which seems a little odd. Then we created read-write executable memory. Still did nothing with it, right? We're not writing anything in there. We're not executing anything. Still gets flagged. Okay, what if I write non-executable data into that memory, but don't try and execute it, don't do anything with it? Well, all the serious detections drop off. We still get a couple warnings. These are the like suspicious program, potentially unwanted program, that kind of thing. But the actual detections start to drop off. So what if we write some actual shell code in there? Well, we get detections, but not that many, right? Well, all right, let's try an encoder. Well, that dropped the detections down, but we're still getting detected a little bit. When we actually start executing it, though, then we see those detections spike back up into the areas that we were expecting to see, around 9, 10, plus some warnings. So from this, you can conclude that creating RWX memory is not the primary thing that it's flagging on, and there is safe ways to use virtual alloc and there's unsafe ways to use virtual alloc in terms of getting detected. It seems to be very contextual, which says that we're not actually getting flagged by pattern matching, we're actually getting flagged by heuristic analysis. It's actually running or emulating the run of that executable and detecting behavior. I was going to have a whole section on this, but it turned out to not be all that useful. For anyone who doesn't know, runtime dynamic linking, Windows provides the ability to, at runtime, load a DLL, grab a function address and call it without having to have that function in the import address table. So this is a way of obfuscating what Windows API calls that we're actually making for static analysis. Unfortunately, this only dropped one detection across the board. So I applied runtime dynamic linking to all of those previous methods, and it uniformly dropped one detection. So it turned out to not be all that useful. But it does, again, clue us in that the old signature-based detections that we used to worry about, that pattern matching where you said, if you just make the code look a little different, you'll get past it, that obviously doesn't hold true anymore. So my next thought was, well, maybe it's just recognizing the shellcode in memory, because we're just shoving all the shellcode in straight order into memory somewhere, whether it's in a new code segment, whether it's in a variable. So what if I scramble that shellcode up, right? So go back to putting in a variable for a minute. And instead of writing the bytes in order, we write them all out of order, and then we create an index map that just tells us where the bytes actually belong, and then we just unscramble it right before we execute it. So it's basically an obfuscation technique. None of the shellcode can't be pattern matched because it's just a random series of bytes at the moment. I also experimented with, well, maybe if we use a jump instead of a call. So what we typically do is we write our shellcode and we dereference it as a function, and then we call that function. Well, what if we instead use a assembly jump instruction to just jump into it as if it weren't a function? So does anyone think that made any difference? Anyone? Hazard a guess? No. Didn't make any difference. Not starting to feel too smart at this point, really. Some of these ideas worked a lot better about a year ago when I first started doing this, and have since pretty much dried up. So the index map made no difference. The jump versus the call made no difference. Again, it's not pattern recognition that is working here. That's pretty much a given. So, all right, what about inlining it? Like I said, we've been shoving stuff into a variable, then doing some dereferencing tricks in C, and then executing it as a function. So executing instructions from data is inherently suspicious, right? That's not a normal thing to do. It's not a normal thing that executables do. What if we instead replace the actual instructions of the executable so that our payload is the instruction set. It is the text section of that executable. And this is sort of my first stab at this idea of blending in instead of hiding, right? So the analogy I think most aptly describes this concept is, imagine you've got a guy who wants to rob a jewelry store, right? Two different scenarios. In one, the guy is waiting for everybody to clear out, and he hides in an alleyway somewhere. The cop walks by and sees this guy standing around in an alleyway not doing anything. He's not doing anything that's immediately recognizable as bad, but do you think that cop is going to come check him out? Yeah, he is. Now imagine if instead our thief in the second scenario dresses up as a meter maid or somebody fixing the street lights, somebody that cop expects to see, something that's completely normal. Cop's going to walk right by because he's already preconditioned to see that guy and say, no, it's cool. That's the same problem with antivirus evasion. Everybody's trying to hide in the alleyway when what they really need to be doing is looking like something that antivirus already expects to be there. So, I don't know how well this actually works looking at code, but basically what I did was I took Metasm, took the payload, and just wrote it in as raw assembly instructions and recompiled in exe. So this is what our first attempt looked like. The second attempt basically do the same thing, but we tried encoding it a couple different ways. Because we control the generation of the executable, it's really easy to set everything as read-writable executable, so our polymorphic shellcode can write over itself, and encoded shellcode works really well. So we tried this with Shikata-Ganai, which is the most common one that everybody uses and knows and loves. Also, Stephen Fewer's new Bloxor encoder. Results weren't really good. So doing inlining actually increased our detection rate by about double where we were right before this. Shikata dropped it, but only dropped it back to the same level that we had a problem with in the first place. And Bloxor was almost as bad as not encoding it. So that was somewhat disheartening, but gets back to encoders do not evade antivirus. I'm going to keep driving this home because I keep seeing it. So that got me thinking. As I was looking at those results, every time we encoded the shellcode, there were a certain set of detections that were always there when we used an encoder. That's a little weird. What if we... Oh, yes. So encoders have always been incidental in their AV evasion usage. They're actually there to remove bad characters for an exploit. Because it makes the code look different, we've gotten past signature detection. But as we said, signatures really aren't our problem. So my next thought was, I wonder if the encoder itself is generating additional detections beyond the payload itself. So what I did was I took a series of meaningless assembly instructions, and it was just push EAX, push ECX, pop EAX, pop ECX. It's basically swapping two registers around, right? 4 or 5 bytes of shellcode, run that through our two encoders, and push that up to virus total. Still get a whole bunch of detections. This should be the final nail in the coffin. If any of you do not believe me that encoders do not evade antivirus, encoders cause antivirus detections. They are suspicious. They look like packers. People have been using packers for, I don't know, 20 years now. They do not work. Do not use them. They are great for exploits if you're doing a memory corruption exploit because you need to get away from bad characters. But if you're doing PSExec and you tell me, I don't understand why my payload got caught. I ran it through Shikata-Ganai 5 times. I will kill you. So, conclusion about encoders. They do drop the number of detections, but they come with their own whole set of detections that they bring all on their own. So it's a complete fail. So what can we do if we're not using encoders? Well, we still want to break up the way that code looks, right? So I came up with this idea of generating, and it's, well, not a new idea, but generating fuzzy NOPs. These are NOPs that are not your standard NOPs. They're not your 0x90. It's actually a series of instructions that at the end have a zero sum. So the registers and the stack all must be in the exact same state at the end of the instruction set as they were at the beginning. And you can just nest these to as deep of a level as you want, as long as you always back everything out at the end. Oh, excuse me. Immediate negation doesn't work because that's really obvious and heuristics can easily just basically ignore it. So if you inc EAX and then dec EAX, well, AV is going to be smart enough to realize that, oh, hey, that's a no operation, really. So we nest about 4 levels deep. So inc EAX, push ECX, do something else, pop ECX, dec EAX, right? And it looks like legitimate assembly instructions. It's a series of operations, but in the end, we've done absolutely nothing. So then you take these and you insert them between all the recognizable sets of instructions in our payload, and hopefully that's going to break up detection, right? Nope. Didn't do a darn thing. we ended up with the exact same results that we got without doing this. So that's a big fail. Okay, one of my coworkers said to me, what about doing code generation? What if you never put your payload in the executable at all? Instead, you have your executable generate the code for your payload. And just jump through these. So basically, the way this works is you take a register, any register. In this case, I use EAX. You zero it out. You encode your payload to a series of 32-bit integers, which you have to actually align the payload first because a lot of them aren't aligned properly for that. But you zero out a register. You set ESP, which is your stack pointer. It tells you where the top of the stack is. You take ESP and you point it into executable memory to where your code is, to some placeholder function that you have that has instructions you don't care about. And then you start performing math operations. So you know that for your first 32-bit integer, which will be the last set of bytes in your payload, and you add EAX that number. Then you push it to the stack. Only your stack is now in executable memory, right? Then you look at your next 32-bit integer and you take the difference between that and the value in EAX and you do a math operation to get EAX to equal that next byte. And you keep doing that over and over, pushing each byte to the stack. So our payload is never actually a part of the executable. It's never in memory until the end of execution. And it just builds that code on the fly. That seems like it should work, right? Your payload's not there to be seen. I see people shaking their head. Oh, yes, and then we jump ESP at the end, of course. Nope. Totally didn't work. At this point, this kind of blew my mind because I've still got in my head this idea that signatures are still a big part of antivirus evasion. That's obviously not true. We're still doing this. Still hiding, right? Because what we're doing still looks suspicious. We're moving the stack into executable memory and then we're writing stuff there. What program does that? I mean, what legitimate developer uses that as a programming technique? You show me the developer that does that, I'll show you a shitty developer. Okay, let's talk about ghost writing. Oh, no, sorry, not that ghost writing. 80s reference, hopefully some people get it. Oh, okay, close enough. Whoops, shit. I am just failing all over the place at running slides. Ghostwriting has been a big thing people have been talking about, especially the past 2 years. Some guys did a really good talk on it at AthCon last year, I believe, and there have been a bunch of blog posts on it this year. Ghostwriting is basically this idea of you take your payload or whatever assembly that you've got running, and you go through it and you say, what can I replace this instruction with? Okay, I have increment EAX, right? Well, what if I do something else that has the same effect? And in our case, it may be multiple instructions to replace a single instruction. One of the big problems with Metasploit payloads when we're talking about dropping to the file system is that they're written for memory corruption, which means they have a bunch of broken assumptions when you talk about dropping to the file system. One of which is that the size of the payload is really important, so we optimize everything to be the fewest bytes possible. We don't have that concern when we're dropping to in an executable. We have as much space as we want. So let's replace all these instructions with multiple instructions that end up doing the same thing, but don't look like the code that you're expecting to see. So, what do you think? Is this blending in, or is this still hiding? Still hiding. And appropriately, ghostwriting with fuzzy nops, because why not, still gets us nowhere. And this is really funny to me because I've seen a lot of people saying, this is the solution. This is it right here. You do assembly ghostwriting and you will never get caught by antivirus. What? That's obviously not true. Again, we're hiding the bad. We're trying to hide the obviously heinous thing that we are doing in memory rather than trying to make it look like a legitimate program. So pretty much all of these techniques have been hiding. Obfuscation, encoding, doing code generation tricks. They're all things that are the guy standing in the alleyway out of sight. Yeah, he doesn't get seen from the street, but as soon as somebody walks past the right way, they're going to be a little weirded out by that guy in a hoodie, you know, just standing in an alleyway somewhere. What we need to do is we need to camouflage ourselves. We need to look so close to a legitimate executable that even if antivirus does figure out what we are, they can't flag us. Because flagging us would mean that they would risk flagging legitimate programs. Because if they start doing that, they're broken. Nobody will buy their stuff if the legitimate programs start getting killed by antivirus. So we want to get right up next to the tools that everybody uses every day and make ourselves indistinguishable from them. Then we can just look at AV and say, you know, come at me, bro. So these are the problems we talked about. You know, our templates get flagged, the stager gets flagged, encoders get flagged, and our very behavior with these techniques is just completely suspicious. No legitimate program would do any of these things. So how do we get around the executable template problem now? Well, in Metasploit Pro, what we've done, and anyone can do this on their own if they want to take the time for it, is we dynamically generate those templates now. We use Metasm to write EXEs on the fly. We generate code paths that are completely random and dynamic. We create random variables and use them to do math operations or whatever so that the memory layout of the executable is different every single time we create it. The execution path is different every single time we create it. There's no way to create a signature like that. You sig one of them, you're not going to catch the next one or the next one or the next one. So that one's really easy to get around. The encoders, just don't use them. That's all this one breaks down to. Don't use encoders when you're dropping to the file system. It's not worth it. It gets you nothing. So the stager. Like I said, all of our shell code was originally designed for memory corruption exploits, doing a buffer overflow. They're highly optimized, smallest byte codes possible. Everything uses block API because we don't know where our API functions are, right? Well, if we're generating the executable, we're a developer at that point. We can use the same techniques that developers use to do linking, and we can get those functions. So payloads from Metasploit as they exist for the stager are really not necessary and dangerous for dropping to the file system. We're using them in a way they were never intended to. So what's the solution for that? We're not going to use the stagers anymore. That is to say, we're not going to use the ones that come as payloads in Metasploit framework. We're going to implement our own real quick. So why not? We're generating an executable from scratch. We have full developer powers. We can do anything we want. So this idea originally came to me because some of my friends who I now see back there from Fail had this idea of basically implementing a stager for the stager, where their code would actually go and get the stager from another source and put it into memory, and then the stager would go back in multiple levels. I said, well, cut out the middleman, just implement in your executable the stager itself. I wish I could take all the credit for this idea, but then it turns out that Egypt and Raphael Mudge had been talking about this like 2 years ago. So I decided to go take another swing back through it and implement our reverse TCP stager strictly in C code, which was a couple of days of me wanting to cut my wrist, because if anyone's ever tried to program to the Windows socket API, it is the most painful thing ever. But all we do is we create a typical C program that creates a socket back to whatever address and port we specify, pulls down a big buffer, virtual Alex some RWX memory, shoves the payload in it, dereferences the pointer to that memory, and calls it as a function. Pretty straightforward, actually. It doesn't take too much effort beyond the, wanting to kill yourself for Windows API programming. The second approach did the same thing, except it's using that runtime dynamic linking I talked about earlier. And this becomes a little more important here. Excuse me. Coffee. Because all of our Windows API function calls are then removed from the import address table, and they're just called directly from memory. So, what do you think, guys? Is this hiding or is this blending in? This is blending in. This is what a legitimate program does, right? It's opening a socket to something, pulling down data, and putting it in memory. There's nothing particularly suspicious about that. The only suspicious part is where it executes it. So we're getting really close to that promised land. Here's what our results are. Reverse TCP without the runtime dynamic linking generated a whopping 3 detections. And I can't remember what they are, but they're all vendors that you're almost never going to see in a pen test. They're the obscure, who the hell are these guys on VirusTotal. Implement runtime dynamic linking, get those things out of the import address table, goes to 0 detections, 0 warnings. All we had to do was implement that same functionality in C. And you can spin that a bunch of different ways. We talked about dynamic executable generation. You apply that same principle then to generating this stager executable. You break up the way that code looks. You do a bunch of other things that are harmless. You kill time so that you get out of a sandbox. How are they going to catch up to this? The only thing left that is at all possible for them to distinguish from a legitimate executable is the fact that we create RWX memory at runtime and then execute that memory we allocated. So this is success at this point, but why stop here? We've got a little more fun to have, and this guy right here in the second row came up with this idea, I don't know, what was that, about 1.5 years ago? Mubix says to me, what if instead of sticking our payload into RWX memory, what if we have the executable have a buffer overflow in it, and then we just have it exploit itself? So Egypt came up with the name for this. He decided that it should be called autoerotic exploitation. I'm going to roll with it. I think it's fitting. It's unnecessary at this juncture, as we saw, because we got 0 detections, but this is a fun little trick we can do, and this again goes to blending in, right? If we're not creating RWX memory, we're running low on time. If we're not creating RWX memory and we're not executing it, we just have a buffer overflow. That doesn't make you malicious. From an outsider perspective, that doesn't make you malicious, right? That just makes you a shitty programmer. There's no end to those. So you're going to see that all over the place. So we did the same thing as the reverse TCP runtime dynamic linking stager. No virtual alloc, but we just do a buffer overflow. We copy our entire stage, all 800,000 bytes of it, to the stack, and then we do a simple string copy buffer overflow to control EIP. And what's great is you don't even have to take Peter's class to be able to do this one, because we're writing the program ourselves, right? So all you do is in your buffer, you figure out what that offset is, and then you printf the actual pointer to your buffer into that section of your string that you're overflowing, and you already know that you have a precise location for where your payload starts. It will execute every single time. Now the part I haven't gotten to get to yet because I ran out of time is to get around DEP, doing a built-in ROP builder. So we build dead code paths, functions that always get conditionaled out, right? So they test a condition and it never passes true, so you never execute that code. but it just emits assembly instructions that are ROP gadgets at various places. So we set our ROP gadgets in locations that we know and control already, and then we have a ROP builder that just goes to those labels and builds our ROP chain for us and adds it into the overflow. Done. What do you think the results of that are? That's right, that's badass. So, fortunately, I seem to be right on time here. Special thanks to a lot of people, no particular order. Egypt, HD, Mubix, Corland Coder, a bunch of the guys I work with, Fail, all the people at AHA, DerbyCon for having us here again, it's been amazing, and everyone else whose name I don't remember who's talked to me drunk while I'm drunk at a conference and given me ideas. There's a lot of you, thank you. And now for something completely different. Thank you.